All right. Yeah, very happy to be here. Also very happy to indeed see a number of familiar faces from last week. I think well, I try to also make the slides in such a way a little bit that it also connects to some of the things that I was actually talking about last week. So hopefully it will be relatively easy to follow if you were here last week. Yeah, that said, I'm gonna try and focus a little bit more on some subtle technical things as well here and there. So please do stop me if things are unclear. It's the first time that I attempt to get some of these things across for an audience like this. So yeah, if I'm not clear, please ask questions. All right, so yeah, let me then dive in. So I'm hopeful to talk a little bit about model-based reinforcement learning and abstraction and the relation between these two. And so, yes, I will actually relate quite closely to some of the things that also popped up in Unstalk. So I think explainability, or what are the causal models, is certainly one aspect of it. But also this question of, well, perhaps in the real world, your MDP isn't quite an MDP, but it still kind of works. And does it really work? And, I hope that at the end of this talk, you are a little bit more assured that in general, things can work. Okay, so yes, then model-based RL, I've been trying to do a variety of different things in the model-based RL space in recent years. So there's also many things that you might have heard me talking about before that I will not talk about. So things like learning partial local models. So I did a lot of work on this, zooming in on traffic settings of some sort. Say, look at one intersection as part of a bigger network. Some of the work on Bayesian model-based reinforcement learning that I'm really excited about, or how good is mu0 really, or indeed, what if you have offline data? All very interesting things, all very happy to talk about them, but I will not talk about that today. I will just try and cover a little bit the idea of, well, doing deep learning based model based RL. Actually, some work that I did with Elise. It gets across, I think, why we need to think a little bit about what are good abstractions, because the method is kind of based on the idea of trying to think of what is a good abstraction in an MDP. And then I will somehow go a little bit further on what I really what I really think we should be thinking about when we try to do model-based RL, right, and have abstractions. Okay, so hopefully it will become a bit more clear. Right, well, just as a general motivation, I think we all like reinforcement learning here, and control, of course, as well, because somehow we believe that this can really help us in real-world decision-making, right? We somehow think that we can use these things in the real world. And often then we think of this, well, real-world problems have a sequential nature. This is why we need to think about sequential action selection. And we end up with problems in reinforcement learning and modeling things like MDPs. Right? Okay. Then, what is model-based RL? Just a little bit of terminology that I always like to do. Sorry for the repeat if you were here last week. Just to make sure that we're all on the same page here, because I think in reinforcement learning, we tend to have a bit, confusion sometimes about the terminology. So I use terminology as follows. So I hope you can bear with me. So everything where the model is available, I tend to call planning. Right, and so if you have small problems, you can do policy iteration, value iteration, these kind of things. If you have large problems, then you might do something like simulation-based planning, right? Or what people have also called approximate dynamic programming or neurodynamic programming, or all these kind of things, motivated by the fact that, well, perhaps I can model my problem, but solving it is too hard. I can't run policy iteration anymore. Then there's also settings where the model really is not available. That is what I really like to think of as true reinforcement learning problems, right? Because then there's no other option than to really learn from real-world interaction. So then within there, I like to distinguish model-based RL, which tries to actually learn a model, and model-free RL, the methods that do not try and do this, right? And so a common confusion, I guess, is that, people somehow mix up these things, where the model is available, where you can do planning with model-based RL, which learns a model. Of course, very typically what we do in model-based RL, we try to learn a model and then use that model for planning, right? And then, well, you can get all kinds of benefits, like perhaps, think about the exploration, for instance, that you need to do. Okay. Why care about model-based RL? I'm going to be a little bit quick here because I think we already had a talk that made very clear that model-based reinforcement learning can actually perform quite a bit better than model-free alternatives. Trying to run model-free RL directly on the real world is typically just not a very feasible thing, right? So we have many successes of these kind of methods. But then if we look at how many samples they need, how much experience they really need to train, yeah, it's just really a lot, right? So particularly, for instance, this DOTA2, this is my own back of the envelope calculation, but it's almost about 10 trillion steps, right? And yeah, that translates just in huge computational costs. And, in the real world's not going to give you this amount of samples. Just as simple as it is. All right. So yeah, then what do we do? Because, well, we started by the fact that we wanted to use these methods for the real world, right? What if perhaps we want to have a shot at adapting to human behavior? They will not give us so many samples. Well, so the idea is that, model-based RL in principle is promising, because somehow if we can learn the model, which might be more sample efficient because there's some particular structure in the world, and then we can use it for planning. Right. Good. Put in a different way, I would say simulators are great, right? If we have a simulator available, we can do this thing that I call simulation-based planning. And what does that mean? Well, you could do something like online planning or model predictive control or deep reinforcement learning. These are all kind of things that you can do with a simulator. And, that essentially means that you're deriving what actions to take now based on the simulator. Good. And so that can work quite well. So this is, well, I'm not going to explain this any further, but this is the thing that I mentioned, where somehow we try to look at one intersection in isolation. So this combines some of these ideas of abstraction. We have a simulator available, a Sumo simulator, relatively detailed traffic simulator, and we can use it to somehow derive these policies with deep reinforcement learning, and then scale up to many, many, many intersections, right? So great. There is, of course, the caveat. I think this is what Jens also was talking about. Of course, somehow we want the real world and our simulator to be sufficiently close. If there's a huge gap here, then there might be some issues to overcome. And yeah, there's lots of things to also say about that. I will not talk about that, crossing this gap with these particular techniques that Jens has been talking about too much. But I will talk about what if our real world or our, is not quite an MDP, actually. Okay, so then we have this perspective of we want to be somehow efficient in terms of sample complexity. We might try and learn a model, and then we can do all the planning that we want, spend as many samples as we want, and do all these kind of techniques. So how do we then learn this model, right? Because, well, there is this kind of like caveat where we want to be able to predict the outcome of all possible actions, right? And also in all possible states of the world. Why? Well, because of what this planning is going to do, right? It's going to consider, well, what if I do this? What if I do that? So this planning might visit all possible states of the world in, well, thinking, say, and look at the outcomes of actions. And based on that, it's going to decide whether it's good, yes or no. But that kind of means that we don't know in advance for which states or for which actions we need to be accurate. No, we need to be somehow accurate for all of them, actually. Right? Okay, well, so then you can also, of course, think of things like exploration and trying to close this loop. Perhaps there's uncertainty about what we've learned about the simulator or the model so far. And we may do some kind of like targeted data collection. What's a question? Yes? So this is a very good question. How is this different from system identification and control? To my understanding, this is not really different. My feeling, but I'm certain, just wrong and ignorant. My feeling is that in system identification, often people kind of like try and consider this really as a offline phase in advance and then derive the control policy, and that reinforcement learning people do try and think perhaps about a little more, but there's also things like dual control, for instance, that actually also take into account this entire loop. Does that answer the question? So yes, it's different terminology, but not necessarily different, I think. Yeah, and so you can even do something like Bayesian reinforcement learning. So this is really, I think, what corresponds to this notion of dual control in control, where somehow you might have some kind of priors as to what is the model of your world, and then you can actually try to optimally trade off exploration, getting more information about what is the true model, and exploitation, exploiting the knowledge that you've learned so far. Okay, so I'm gonna try and zoom in a little bit on this in the rest of the talk, right? So, and yeah, somehow we hope that this would work for all actions, or we want to know what is a good model. And we also want these things to kind of work for abstractions, right? Because otherwise, does model-based reinforcement learning really work? Because the models that we use are abstractions. It's my argument, right? Like we are trying to model reality, but reality rarely is an MDP. So if we apply, say, tabular model-based reinforcement learning, just from Russell and Norvig or Sutton and Bartow, we have projected our abstractions onto reality, and are hopeful that perhaps this is kind of like an MDP, but it might not quite. And if we do deep model-based reinforcement learning, these methods are going to learn their own abstractions, right? But again, there will be abstractions. So we would be hopeful that things like model-based reinforcement learning really work with these abstractions, right? But there was surprisingly little theory about this that we could really find. And I'll try to get to this in the more second part of the talk. It's really not so simple to combine these things directly. And just as an example, we can consider something like RMAX. It's my favorite model-based reinforcement learning algorithm because it's simple and nice and old. So, I like it. And not everybody might know it, but it's a very simple algorithm. It does just this kind of thing. It considers initially all states unknown, and it's going to interact with the environment. It's going to store the rewards, store the transitions. And once we've seen a particular transition, a particular state action pair sufficiently often, right? So we can somehow derive what M should be to be certain, confident enough. Then we compute, well, what was the mean reward and what was the empirical transition function? Now we know this bit of the model. The rest of the unknown model, we assume it's going to be great, right? You will get the maximum reward and you will stay in that state forever. So with this model, this is now an optimistic model, you can plan. And what happens is then, you end up visiting precisely all those unknown states. And so you're going to explore in a directed way, right? I think, yeah, it was just a beautiful, nice idea. I always explain that to all students. It's just, I don't know, it's nice. And then there's some theory, right? Because, well, you can somehow, the details here don't matter, but you can somehow say, well, with probability, 1 minus delta, this is going to lead to a good policy, right? It's actual good theory. And that's great, right? Gives us confidence that this works. But yeah, this is really based on the fact that, you know, we are in an MDP, right? It's not quite clear that this would also work in abstracted models, which are slightly like an MDP. Okay, all right. So let me explain a little bit of the deep model-based reinforcement learning that, well, mostly Elisa, I shouldn't be taking too much of the credit. She's right over there. Yeah, wave. yeah, that's Elisa. Great. As done, because it kind of also gets across somehow some of these ideas of what might be good abstractions, right? Okay. Because, well, so you can do, of course, something like the World Models paper from 2018 that essentially said, well, we're gonna somehow build models of the world, taking in images, doing them through a autodecoder. So we'll get some latent encodings Z, and they might just be good, right? So we just take those representations and then learn on top of this, perhaps transition models and reward models, and things will be great. But of course, yeah, there's a lot of details that you might need, and it might work quite well. I'm not saying that this is bad per se, but the question, of course, is okay. Then what is that representation really? Is this really good for RL? Is this really good for reinforcement learning? Does it really represent well an MDP? Okay, so yeah, like I said, it can work well. I will not argue with this. But if we look at kind of indeed the type of representations that you may end up learning, so this is a very tiny example. The person needs to get the key and then go to a particular corner of the image, I believe. Yeah. You get these kind of like latent state distributions where, yeah, it's really not clear how this space is organized, right? It's really difficult to interpret. And so even if you can do some kind of planning, well, yeah, who knows? It's a bit difficult, right? So it's not really clear if these are really the best abstractions. And so perhaps we should think about, well, what are good abstractions? And so when we started doing that, we thought like, well, okay, let's try and base ourselves on some of the theory that we know about MDPs and trying to make them smaller, essentially. All right, so that brings us to these notions of MDP bisimulations, or stochastic bisimulations, or Lex bisimulations. There's all kinds of terminology that people use for this. But MDP bisimulations and MDP homomorphisms. All right. So before I dive in, let's then think about what is abstraction, right? Abstraction or state abstraction, as we will talk about it, is essentially partitioning of the state space. So we might have these states, all the black dots. Somehow we partition the state space, and we derive now a new set of abstract states, right? That essentially correspond to clusters, the underlying state space. Right, and then so if we have an MDP, somebody gives this out to us, you know, we have this MDP, and somebody also gives us this abstraction function. What we can then do is construct a abstract MDP, right? So somehow we decide upon a weighting function. So for each cluster, somehow we will assign some weight to all the states in that cluster. That's what this omega phi s does. And then we can construct an abstract transition function and an abstract reward function just by summing over the states and weighing them with this weighing function. Right? That's just how we can construct an abstract MDP. Okay, so that's great. And then if you somehow have abstractions that are sufficiently good, that can lead to really good behavior, right? For instance, an exact abstraction or exact MDP bisimulation, or an exact stochastic bisimulation, we get when the abstraction is as follows. whenever S1 and S2, two states, are in the same abstract state phi, right? So whenever we put two things in the same cluster, they should have the same rewards and they should have the same abstract transitions, right? So the probability of going to some cluster phi prime from state S1 and from state S2 is going to be the same for all actions. Okay. Yeah, sorry. Brushing up against the mic a bit, I think, but I don't know if it's so bad, then I will fiddle more with it. All right, yes, right. And this again is just this summation over the underlying states in the cluster, etc. Okay. Yeah, so that's a exact abstraction. This is also called in the literature a model irrelevance abstraction. And then it implies the same Q values. Yeah, it just implies that everything is preserved, right? It's really exact. We're just now created a smaller MDP. Great. Then, of course, that's not always easy in practice. So you could also have something which offers some approximation, introduces some epsilon, say, to still be approximately a exact abstraction. The idea is really, again, we're going to look at state 1 and state 2, and if they're in the same abstract state, their reward should be sufficiently close within a particular epsilon r. And their transitions should be sufficiently close, also within some epsilon, say. And then if we use a model that we construct like that, and this holds, then you can show that you, when using planning, you will also have bounded value loss. And then yeah, you get these types of statements where the optimal value for a state and the value that you will use by using your abstract policy is somehow bounded by some constants, etc. Yes, question? Yes. So the question is, well, you might ruin that this is an MDP, and that's precisely the point that we will get to. Yeah, no, that's absolutely right. Right. So the thing is, okay, somebody gives us an MDP and an abstraction, and the abstraction is of this quality. Then we can construct this abstract MDP again, right? We create this weighting function, we construct an abstract MDP, and if we use that for planning, we know that this holds. But of course, the original thing is not like an MDP. Okay, let me see. Well, this notion that you can have an approximate abstraction motivates the idea of perhaps also thinking of these kind of like criteria as a sort of metric, right? Somehow if we optimize this metric, it's sort of a metric, so somehow this is sort of a distance, not exactly a distance, but where yeah, we try and perhaps think of, well, two states are very different if they have very different rewards and very different transitions. But if they have very close rewards and very similar transitions, that distance is small. Right? So you can try and now perhaps optimize perhaps your abstraction, right? Great. Well, that's of course precisely what we would want for deep learning. And so that's precisely what Elise did. There was one more twist. So here we were saying, well, this needs to hold for all actions. But actually, you can also think of different situations where different actions might actually lead to a similar type of effect, right? So imagine moving down here or moving right here. If the goal is here, that actually has sort of a similar effect because we're moving towards the diagonal, right? So then you can somehow take this problem and try and construct a other problem with a smaller state space and somehow a modified action space also, if you will. Right, and that's what happens in MDP homomorphisms. And so then when we put these ideas together of, well, perhaps having this metric and this idea of these homomorphisms, yeah, we end up with this formulation that we introduced, this kind of MDP homomorphism loss that looks a little bit complex. I will not go through all the math here. But the idea is just that, well, if we have somehow a particular state here and you're making an actual transition in the world, and we have this state and we would encode it to a latent state, and we have this state and we would encode it to a latent state, well, then of course we would also want that in the latent space there would be a transition there. Right, so this kind of like consistency, or it's a commutative diagram of what somehow needs to happen here. Right, so this you can then encode, and you put it together with kind of like this loss on the rewards, right? So we want the rewards to be similar, we want the transitions to be similar. That's all being put in the loss there. And then in order to actually get this to work well, actually the training with this contrastive loss term turned out to be quite important to actually get this to work, right? So yeah, you sample states which are like a next state. Those are the positive examples, but you also sample states which are not the next states. Those are the negative examples. And yeah, you add them somehow into the loss. Yes. So, well, these are essentially just distances that we put. So this is the distance that we put on reward. This is the distance that we put on the transitions. So yeah, here, there, these terms. Well, also here we have a term for the rewards and a term for the transitions. That's, yeah. You can weight them also in some way. There's some tweaking, of course, that you can still do there. Okay, well, so I mean, I don't want to go into all these details here. I don't think that's important, or it's helpful. But what I really think is important is that, so if you now put more of these constraints on your latent space, you get reasonable representations, potentially. So this is what we achieve for the same type of problem. So indeed, there's somehow the lower grid where we first go to the key, then we transport to the other key, and you walk to the right corner to exit the maze or something. That's what it more or less was. But so now this is sort of interpretable, and not only is then interpretable, you can now actually also use this for planning, right? So you can actually take such a representation, do some discretization. Normally, when I give this talk, I always said, well, that part was a little bit ad hoc, and there's probably improvements possible there. I would never do that when Elise is present, of course. But yeah, so you know, I mean, the nice thing is you can take this and you can discretize it, apply just plain value iteration to it, and get something, right? And so that leads to, so it's the line here, right? So lower here is better, it's episode length. It's the line here. This is our result. And then if you take those other kind of like encodings, right, that are a bit more messy and things, then it just, you need to do much more training and things before you can get things to work. Okay. Right, so yeah, is this a success story? I guess sort of empirically, it's nice. We collected data, used it to learn a state representation with this MDP homomorphism loss, estimated a model on top of this, used it for planning and hope for the best, and it worked well, right? Good. But yeah, wouldn't we like somehow a kind of theory that really establishes this to some extent, right? If our abstraction is quite good, your value loss would be limited. Because that's what we had in the planning case, right? Okay, so there's some subtleties when you're trying to learn MDPs that I hope to still get some bits across about, right? And this just really has to do with learning these kind of like conditional distributions, right? So somehow, like I said, we want to have some estimates of the transitions and the rewards, and then perhaps some confidence on the accuracy of these in order to make some statements. And of course, you know, actually there was also this issue about causality, right? We really want to have these probabilities of S prime given that we somehow initialize the world in some position and take an action. That's really what we would like. But in MDPs, they're great. We actually don't need to worry about that. We can just show that, yeah, these probabilities are the conditional probabilities in these settings. Okay. Well, right. Okay. So if we somehow do this, we estimate these conditional probabilities, yeah, then we get these typical results, like for instance from Weisman, that say, well, if we estimate the empirical model and there's a true model, and then the L1 distance is defined as this summation, and then that L1 distance, actually we can bound, right? So the probability that that L1 distance is bigger than some epsilon is going to be smaller than some quantity, depending on how often did we experience the state action pair. Right? So that's great, but it does require these samples to be IID, right? Independent and identically distributed. But if we get our samples from a Markov chain, they're not necessarily independent, right? So let's see. If we, okay, I needed to adapt this, I think. I apologize. But so, in this example, so we are in state 1, and then in state 2, and then in state 1 again, and then state 2 again, and state 1 again, say. So somehow, knowing about what state we jump to actually might have given us information about what state we jump to here as well, right? So even though the thing is Markov, somehow the future outcomes that we observe actually, are not independent of the things that happened earlier. Sorry. So here, indeed. So the probability somehow that S2 equals 1, not knowing anything about the future, is actually not the same as when we would know things about the future. Right? And that can be quite important. So let's consider this Rmax again, right? So this Rmax is kind of like gonna have this magic value of m. Well, if we visit it exactly m times, then we're gonna compute these means. And then, we hope that this is gonna be accurate. But if we collect the data in this way, yeah, perhaps actually this might not completely hold. Right, so Strela Littman had this nice example. Let me see, I have some hidden bullets again. This kind of very simple MDP, right? We start in state 1. With probability 1, we go to state 2. Then there's a 50-50 chance. Either we go back to 1 or we go to 3. But when we go to 3, we stay there. So now what kind of probabilities will I estimate given that I require m equals 5 samples? Right? So somehow that implies that, I should have jumped back a lot of times. And then I'm gonna actually, estimate the probability of going to state 1 to be at least something like 80%, right? Top of my, well. Right, okay, so yeah, anyway, so it's not independent in any case. Right? Yeah, so what then can't we use these bounds? Well, actually, in the same paper, they show that we can somehow still use these bounds. And things will get a little bit subtle, and I think I have only 5 minutes left. So let me hurry up a bit, but they kind of say, well, we can still somehow use these to upper bound particular probabilities. Right? So as long as they come from an MDP, though. Right? So, but what do we have when we apply this to settings with abstractions, right? Abstractions, models are abstractions, and abstractions, are really kind of like, oh, sorry, this is a bit weird again, are like POMDPs, right? If we somehow apply abstraction and then collect abstracted states, and estimate now these models based on these abstracted states, that's kind of like a POMDP. Right? We get observations. Those are the abstract states. We don't know what the underlying state was anymore. And yeah, so okay, so well, an abstract MDP we can construct and we can plan with it, but that abstract MDP cannot be really experienced. Right? That's at least how I interpreted the question a little bit earlier. Somehow we are in a POM-DP really, right? Yeah. So okay, so when the MDP isn't known, we get this kind of setting, and you know, we cannot directly conclude that all these theorems will then hold. And yeah, so that loophole argument that Strelen-Littman found also doesn't apply anymore, right? Because we are now in a POM-DP. Yes, a question. Yeah. So absolutely, abstract MDPs, robust MDPs, model interval MDPs. There's a whole zoo of things that are a little bit related, and there's also some minor differences. Happy to talk, but let me make sure that I don't take too much time from Davide there. I'll get in a row. Yeah. Well, okay. So I think I've made the main argument, right? So the problem here is that so somehow what we're trying to do, say now, is, you know, estimate this transition, right, from well, abstract state equals 2 to some next abstract state, and we observe that again over there, right? So we somehow try to estimate this quantity, say, and then as before, of course, these things are not independent of each other. But really, there's more issues going on now. They're not evenly identically distributed, or not even Markov, because it's really a POM-DP. Right? So, okay. Should we give up? No. So Rolf did a lot of puzzling, and he was able to come up with a solution by building on these martingale bounds. And so what we can show is that the empirical model, the empirical abstract model that we would compute in this way by just counting the abstract state transitions, that is going to be close to another type of model. So this is just kind of the empirical model that we will estimate, and this is an abstract MDP that we would form if somebody gave us the MDP and we would observe the underlying states, right? So we can define that MDP. Somehow we went out in the real world, we stumbled on real states. We only logged these, but there were real states, right? They were there, we did visit them, they did give rise to the observations. And if we would know those states, and we would know the transition model, then we could construct an abstract MDP with the appropriate weighting function, as you know, corresponding to how frequently we visited those. And these two can be bounded, the difference between these two. And so that's great, because the difference of this with the true model can also be bounded. That's what we saw before. Right? So now we are in a setting where we can say, okay, we can bound actually the total difference to the true underlying model if we apply these kind of constructs, right? Yes, so that's what I just said. So that gives us a total loss on the bound of doing this reinforcement learning from abstracted observations by having an additional epsilon term, right? So you look at your model-based RL paper, it specifies some particular epsilon. Now you're gonna need to add another epsilon, which is gonna depend on how good of an abstraction you have, right? But yeah, then you can kind of do that. And so, of course, you know, we applied that to my favorite algorithm, RMAX, which, you know, it's of course a bit old. And doing this for newer methods is certainly something that people should do. Happy to talk about that. But yeah, that we didn't do yet. Right. So yeah, I hope this is reassuring. Assuming your abstractions are quite good, your value loss will be limited also in model-based reinforcement learning. Making sure that they are quite good, that's still also an open question, but okay. Let me stop talking. I think I took enough time. Thanks for listening.